Hello, this is Brian Winkle. I'm the director of SIMIODE, which is a systemic initiative for modeling investigations and opportunities with differential equations. This is a project we're working on and hope to have mounted at the website www.simiode.org later in the summer of 2013, and to probably be available for use by faculty who wish to teach differential equations using modeling and technology as the driving and sustaining forces for both learning and doing mathematics of differential equations. So at that time, you can check us out. In the meantime, if you want to be put on our mailing list, or you want to learn how you could contribute your applications, the things that excite you in this learning community, which is what we're building in SIMIODE, you can write to me at brianwinkle@hvc.rr.com. What we're going to do is we're going to look at the modeling of a spring mass damping system, and we're going to do it from soup to nuts. We're going to model this with the traditional second-order differential equation that students would develop from a free body diagram using Newton's second law, which says that the sum of the external forces applied to the mass is equal to mass times its acceleration. Then we're going to collect some data. In our case, we're going to have collected it beforehand, and we're going to offer the data in this notebook, and we could also offer it in any file, including Excel. And then we're going to show in this session how students might proceed to analyze it and how they might communicate that. So let's begin. This is the apparatus. We have a spring. We have a mass, in this case a 200-gram mass, and we have a motion detector. This is a motion detector from Vernier, pretty standard. We have it set to sample the position of this mass about 50 times a second. And we're going to take 30 seconds worth of data, which is an absurd amount of data. But let's proceed and see what happens here. This entire notebook has been evaluated, and here you see the first cell, which is 30 seconds of data at about 50 times per second. So we're going to close this up and point out that the particular mass we used was 200 grams. The spring was rated at 15 newtons per meter. We actually found out that the spring constant was a little higher than that, so we're not so sure of the manufacturer's claims. But the mass was right on because it's a pretty solid standard piece of mass, brass mass. Okay, so what we have here is the data has been input. We have 1,500 pieces of data. We're taking the average value to be about 0.3 of a meter off the ground from the where the sensor is up to the mass. And we're going to be massaging for a few frames here the data so that we can get it in a nice form. So that's what these are all about. And we're putting it into an array to use for that. Here's a plot of the data over 30 seconds. You can see the oscillations. You can see that it's realistic data. It doesn't go down so purely. It's certainly got some bias in the sampling. But we'll be seeing more and more of it. Here's a plot of the data for the first 4 seconds. So this looks like an oscillator. We surely can't see it dampening quite here, but we could go a little further and maybe take a look at that. Here again is the damping effect, and again the sampling. So we're still massaging the data to get it to the point where we have a nice starting value, and the displacement is, this means that it's about 0.5 of a meter above the equilibrium value or the average value. And so down is up, if you will. And what we're doing is here we're computing the velocity, the initial velocity, by taking the velocity between the second and third time observation. and taking the velocity between the first and second observation and averaging those to get a smooth initial velocity for our differential equation. We have an initial position right here, and we now have, instead of 8 seconds worth of data, we've got a few less data points, so we're up to about 7.96, more than enough sets of data points. Here's what it looks like over the 8-second data point. At this point, we actually go to the differential equation. We get this differential equation because of Newton's second law, as we said, and this is the mass times the acceleration equals minus c times y double prime minus k y itself. And when we put that on this side, we get the plus. These are the numbers that we have for initial position and initial velocity. We solve this differential equation. We can actually solve it again here to show you this is live. And you'll notice the parameters m, c, and k are still in there. These numbers, of course, coming from initial displacement and initial velocity. This is very important. This is the sum of the square errors between the model, ys is our model, at this particular time, for I goes from 1 to the length of the data set, differenced from the actual observed displacement, and then squared, and then adding all up. And because Mathematica will have a few very, very stray small values of I, usually with very small numbers, we're essentially saying truncate those out and just give us the real numbers. There's really no loss in doing that. So what we did now is we said, well, we had 2/10 of a kilogram, or 200 grams mass, and we used a little high school physics lab to get the function of the weight versus the displacement, and we found out that the spring constant was about 17.306 newtons per meter, so we're using that. And so the only parameter really up for grabs that we can't measure is the damping coefficient, which is in newtons per meter per second. So if we create that sum of the square function, we plot it, we see that there is a value of c which minimizes the sum of the squares, and that value of c is about 0.158. So it says if c is 0.158, etc., newtons per meter per second, that will minimize the sum of the squares between our data and our model. Here we have an example of plugging that particular parameter value in for C, and we create a model using the letters K, K, C, C, M, M to distinguish them from the more generic ones, M, C, and K, and we plot the solution, and it's damped. That's good. The bad news is it's overdamped. It's damped too much in comparison to the data. So we've got to look at something else. What we'll begin to do now is go back to the model and say that there are 3 parameters, M, C, and K. Solve the differential equation in terms of those 3 parameters. Again, these numbers represent the initial conditions. And let's see what we can do. Here's a powerful tool in Mathematica. It allows one to play with the parameters. And if we were to set, say, the mass at around 0.2, and we were to guesstimate by playing, say, at 0.005, and we were to put this in at around 617, we would see that not too bad, that this solid line is the model with these parameters in it, and it comes pretty close to this. We can also see that changing the spring constant, that is the ability of the spring to retract, certainly changes this period, and that is well known, and you can study that in general. And of course, changing the mass changes things, and changing the decay constant, changing the dampening factor, does exactly what you say. That is what you might think. So let's go on then and build a model with these values that we got from just tweaking around the previous manipulate. And when we look at that model, it comes out to be this. Doesn't quite look like it's damping, but it actually is. And of course, if we went further, we'd see that. Let's take a look at the model that we just had over the data. Looks pretty good. The model seems a little bit high here, and maybe we might want to look a little further. Okay, so we go back to the general model again. This time we're going to try to get the Mathematica to minimize the sum of the square errors and get the values for M, C, and K on its own without us having to prescribe anything for M, C, and K. And of course, we'll give the algorithm a good starting value based on what we know already. And what we come up with is pretty consistently that the mass is a little more than that, at least in this predictor. And the spring constant is about what we had suggested. And this is a model right in here. Now, of course, you see good old e to the I theta, which of course is no more than cosine theta plus I sine theta, according to Euler's formula. And so while all this complex arithmetic is here, it really shakes out to be real when it comes down to it. And in fact, here's a plot of that solution for those parameters. And we take a look at that plot over the data, and that looks spot on, as they say in the BBC. Again, kind of damping, coming pretty close. And if we look over a long period of time, what we'll see is that this is what the model predicts over the full 30 seconds. And if we dared to plot the full 30 seconds of data, we can see that it tends to have that capability. It rides a little high here, but it certainly has the damping capability in the gentle damping slope this rather bouncy spring has. So what's our conclusion? Our conclusion is that we were able to model a spring damper. We were able to collect some data. We were able to estimate the parameters of the model, namely the mass, the damping constant, and the spring constant, given the data and given some initial position and velocity, which we computed from the data, and it looks like we have a pretty good model. So we feel that students would experience this whole activity and it would reinforce the building of the model with the actual reality so that it convinces them that the differential equation is a viable tool for studying science and engineering. We hope you enjoyed this. And again, if you're interested in SIMIODE, we encourage you to go back to the first panel and learn more about it and get in touch with us. Have a good day. Take care.